Goldbeck conjecture. So there is a very interesting story about this conjecture. So first, what is conjecture? Conjecture is that result which cannot be proved in journal, but we can verify it with the help of examples. So in a letter to Euler in year 1742, Christian Goldbeck guessed that every even integer is sum of two numbers that either prime or 1. A somewhat more general formulation is that every even integer greater than 4 can be written as sum of odd primes. Let's have we have numbers 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So how we can write 2 as sum of two numbers either primes or 1. We can write 2 as 1 plus 1. So 4 as 2 plus 2 as well as 1 plus 3. And 6 as either primes or 1 and prime. And 20 as 3 plus 17, 7 plus 13, 1 plus 19. So there are so many examples which can verify Goldbeck conjecture, which says that every even integers is sum of two numbers that are either prime or 1. Another interesting fact related to this is that Euler have never tried to prove these results sent by Goldbeck, and in his reply to Goldbeck, Euler sent his own conjectures to him, which can be easily verified in this example. One more interesting fact about Goldbeck conjecture is that it has been verified by computer for even integers less than equal to 4 into 10 raised to power 14. It has been verified for this number until. Next definition we have for twin primes. A successive pair of integers p and p plus 2 are called twin primes if both p and p plus 2 are primes. So we have so many examples like 3 and 5, 5 and 7, 11 and 13. All these are pair of twin primes. Now we have some properties of twin primes. Prove that product of twin primes is 1 less than a perfect square. And we know let p and p plus 2 be twin primes. Then their product may be written as p into p plus 2 is equals to, this is p square plus 2p. Let's try to complete the square. We will add 1 and subtract 1. Very easily this is written as p plus 1 whole square minus 1. To clearly which is 1 less than a perfect square. Hence p into p plus 2 is 1 less than a perfect square. Next question, for p is strictly greater than 3, show that sum of twin primes is divisible by 12. So let, as per definition, p and p plus 2 be twin primes and their sum is p and 2p plus 2 as, this is 2p plus 2, which is 2 into p plus 1. Let's denote it by t, say. And we want to prove this sum is divisible by 12. This is what we have to prove is that 12 divides t. So this is our aim here. Since p is odd, therefore p plus 1 is even So which further means p plus 1 is 2k for some k belong to z. So as t is 2 times p plus 1, the putting value of p plus 1 here, it is 4k, which clearly means 4 divides t. So we want to prove that 12 divides t. How we prove this? By proving that product of 3 and 4 divides t. So we already proved 4. Now we try to prove that 3 divides t by division algorithm. When we divide any number by 3, it is of the form 3k, 3k plus 1, 3k plus 2. But 3k cannot be prime, so we are left with only two possibilities, 3k plus 1 and 3k plus 2. So first let p is equal to 3k plus 1. So which means p plus 2 is 3k plus 3, which is a multiple of 3, not a prime. Not a prime. So means p cannot be 3k plus 1. Second case, 3k plus 2. Then p plus 2 will be 3k plus 4, and t becomes, this is 2 times p plus 1, putting value of p here, this is 2 times 3k plus 3. So clearly 3 divides t. So we already have that 4 divides t, 3 divides t, and GCD of 3 and 4 is 1, imply their product will divide t. So which means 12 divides sum of twin primes. Answer. Find all twin primes p and q for which pq minus 2 is prime. Now p and q are twin primes. That means for p to be prime, for p and q be twin prime, p is p and q has to be p plus 2. Then pq minus 2 will look like p times p plus 2 minus 2, that is p square plus 2p minus 2. Now let's try some examples, like if p is 3, then q is 5, then putting value 3 and 5 here, 3 into 5 minus 2 will comes out 15 minus 2 is equal to 13. So we get one pair, 3 and 5. Now let's try out options p is strictly greater than 3. So by division algorithm. When we divide any number by 6, if it is prime, so we are left with only two options, 6k plus 1 and 6k plus 5, because in all other cases it's not a prime. Now for first option 6k plus 1, then p plus 2 is 6k plus 3, which is not prime. So this is rejected. Now second option 6k plus 5, we have 6k plus 7 here, and here we have 6k plus 5 into 6k plus 7 minus 2. After simplification, this will comes out 36k square, 72k plus 33, which is a multiple of 3, 12k square plus 24k plus 11, which is not prime. Which means for p strictly greater than 3, there is no twin primes for which pq minus 2 is prime. So only pair is 3 and 5. answer.